Right there. Hello, everyone, and welcome to the first Cambridge Zero Research Symposium on Zero Carbon Energy Transformation. I know that there's still people filtering in as we speak, and we're now on about 60 attendees, but we're expecting a few more, I think. But we'll just get started just with a brief introduction, and then so that people have a bit more time to get in before the first speaker. The topic of today's symposium is zero carbon energy transformation. This is the first of our 6 research themes that we're organizing symposia on over the coming 6 weeks. For this week's symposium, we have 4 keynote speakers who will be presenting. The program is shown here. So we're starting off with David Reiner on the political economy of industrial decarbonization. Then we've got Sam Stranks on next generation photovoltaic and lighting technologies, Siân Dutton on magnetism as a probe of batteries, and Laura Torrente on power to X and X to power ammonia as X factor. We'll then carry on with 4 postgraduate and early career presentations, starting with Molly Haugen, who's talking on evaluating hydrogen and electric energy systems as decarbonization options for transport. Aidan Parkinson will be speaking on social costs of carbon state of the art. Collin will be speaking on redefining the Haber-Bosch process for green ammonia synthesis, and Sergey Kolesnikov will be speaking on how technology spillovers can contribute to clean energy innovation. So that's the program for today. After each speaker, there will be time for Q&A. You will be able to submit your questions using the Zoom Q&A function, which is enabled on the webinar. You can upvote questions. So if a question has been asked that you would like answering, please vote for that question to come up, and then we will try and get it answered. I will moderate the questions as they come in and put them to the panelists. And if we don't have time to answer all of the questions that do come up, then we will collate all the questions and answers and circulate those with attendees after the event, in case we don't have time to get through them all today. Then I also just wanted to highlight that, as I said, this is the first of 6 research symposia. So we have the following 5 symposia in the following 5 weeks on the other 6 research themes that Cambridge Zero includes in its research portfolio. So next week we've got the symposium on health and society, and so it would be great to see you guys there as well. And so please do sign up through our website, which is there at the bottom. And then in the following weeks we have resources and production, resilient futures, transport, cities and infrastructure, and carbon drawdown and climate repair. So please do sign up for those symposia as well. And finally, I just wanted to also add other ways of continuing the conversations starting today. So later this week, there is another event being organized by the Energy Transitions team on the Energy Transitions discussion series. This is happening this Friday, and you can sign up at the link shown there. And I'll share this again at the end of the event and after the event. And our next symposium on health and society next week. Please do also sign up to our mailing list, our Cambridge Zero research mailing list, if you haven't already. And you can follow us on Twitter as well. So those are ways of continuing the conversation after today. So I think we've got 100 people on the webinar now. So I think we can get started with our first speaker. So I'd like to introduce Dr. David Reiner from the Energy Policy Research Group, and he'll be presenting first today. So David, please could you share your screen? There we go.
Great, hopefully that's working.
Yeah, that's fine, yeah, thank you.
So thank you, Eric. Thank you for the invitation. It's a pleasure to be here. I'm going to be talking sort of at a high level about some of the work that's going on around the UK in terms of industrial decarbonization, and try and understand how it is that we've wound up where we are at the current moment. I've been working on carbon capture and storage and the politics, and as well as sort of the techno-economics surrounding it for for a number of years, and I'm left feeling often a bit like the classic Peanuts cartoon of Charlie Brown trying to kick the football and Lucy kind of taking it away each time. I'm sort of in the advantageous place of being an observer, but I think for those who actually have been involved and more vested in these projects, I think it has been a series of longstanding frustration. And so I wanted to start with a couple of basic principles, which is that if you look over the last, well, couple of decades, you would see that most outside observers, most analysts, the International Energy Agency, our UK Committee on Climate Change, the IPCC, will argue that carbon capture and storage is a critical element of decarbonization, and that's particularly true in energy-intensive industries. Unfortunately, most of those scenarios actually don't recognize other things, which is how do you cobble together the sort of political support that's necessary to underpin those projects. And so therefore, we've seen kind of a long-standing, as I said, history of failure to meet these prognostications, these expectations for the level of penetration of carbon capture and storage that are needed. And you see this even most recently in the last UK Committee on Climate Change report just this past month, where they argue that CCS is particularly important in manufacturing because it can address emissions that can't really be addressed in any other manner. But just because that's true doesn't mean that actually we end up building these technologies. And if you go back to 2013, you'd see the IEA laying out a roadmap which would expect by where we are today in 2020, sort of many hundreds of millions of tons of CO2 being captured a year. Whereas instead the number is probably a tenth of that, and the pipeline itself is quite weak. The expectation is that, or that has always been, that a good chunk of it would come from energy. So you see the gray for coal and the green for bioenergy, but that maybe half of the capture would be put on large facilities like cement or chemicals or refineries, so on. And when I did a snapshot paper of this in 2016, I sort of documented what was a litany of failure. There were some small projects that went ahead, but mostly what we saw were a lot of X's in particular, and notably the UK, which has had a rhetorical commitment to CCS for many years, ended up canceling their project. There were actually two competitions. The first under the Blair government, which was an offer of £1 billion that was intended to be a light to China and focused on coal CCS. The coalition government made £1 billion available in 2011, but by 2015, the Chancellor George Osborne canceled it, and so it seemed that we were in sort of the doldrums, that the expectations of what we needed weren't being met by the politicians, by the policymakers who were meant to be putting these projects forward. I think there's a long litany of reasons why that's the case, but I think a couple of them I'd highlight. One is Lord Oxburgh referred to CCS as an orphan technology, and I think that is one of the challenges, that you haven't had strong proponents. What carbon capture and storage does is add cost to existing industries, to power plants, to steel mills. And so their preferred option is always to continue doing business the way they always have. Whereas other technologies, like in nuclear or wind, you actually will have advocates who want the green alternative. I think other big challenges that you've seen on the political side is that some of the advocates, some of the proponents have been not been seen, or genuinely not green in their aspirations. So the George W. Bush administration, the Australian government, much of the coal and the oil and gas industry have been proponents of these technologies. And so there's been a view perhaps that CCS is either disingenuous or diversionary or a white elephant or all three. What I'll come back to, though, is one of the big barriers has been there hasn't been any effort to think of this in terms of industrial policy. And the focus in both the first and second competitions in the UK, for example, were to drive down prices and drive down costs rather than think of it in terms of regional policy. And so I think finally one of the big challenges is it requires a significant amount of infrastructure. And to do that, the question is, well, who will support the sort of the pipelines, the storage facilities that would be needed to store the CO2. And sort of out of the ashes of the failure of the second competition, Claire Perry, who's the energy minister at the time, put together a cost challenge task force. And one of the things that I served on this task force, one of the things that we did was to identify a number of ways in which we could sort of change the approach. One was to develop a new business model for transport and storage. But I think maybe most importantly was this idea of focusing on clusters and focusing on these CCUS clusters rather than individual power plants as the basis for taking action. The other point, which is mentioned at the end, is this idea of the UK could be a global technology leader. And so here we are several years later, and the 10-point plan that the government released just this past December, we see that point number 8 is this focus on carbon capture and storage with a new £1 billion that has been found. But the entire kind of discourse, the rhetoric around it is about these so-called super places, which I sort of cringe at. The idea that the Northeast, the Humber, the Northwest, Scotland, and Wales will be those areas that will be recipients of this funding, and they won't be kind of thought of as in terms of individual projects, but in terms of the wider cluster. So there are a couple of reasons, to explain what has changed. First is that probably for the first time since the 70s, industrial strategy came back into vogue. Theresa May brought this back when she took over as Prime Minister, and Boris Johnson has continued that commitment. I think the other big change, and in some ways, if you have an 80% commitment, you should need to be doing a lot. But I think the nature of a net zero commitment has meant that no industry could hide, no sector could hide, and everybody had to try and at least put forward some sort of credible pathway to deep decarbonization. And then, in my view, maybe most importantly, the changing politics of this. So post-Brexit, so it's not a coincidence that the project for last competition was canceled before the Brexit referendum. Once kind of the repercussions of that referendum were felt, there was a recognition that I think both major parties needed to think about how to address the concerns of these leave voting regions, because it's not just about the EU. And they also needed to look at look for export opportunities. And so one of the striking things that if you look at the last election results, you'll see is that the conservative gains came in kind of the most manufacturing heavy regions. So the so-called red wall seats aren't a perfect proxy, but they actually are in the same area, same regions, as where many of these industrial clusters are being proposed. And so if you look at where those clusters are, they're up in Grangemouth in Scotland, Teesside in the northeast, Humberside, South Wales, Merseyside, and so on. So this is just a different way of showing it. You get a range of different industrial emissions that are produced. And the goal, and the new goal, I think, that the government has set out is to come up with a net zero cluster by 2040 and to launch 4 major industrial clusters by 2030. And the seed funding for that, at least, has been 170 million pounds of investment from the government. That's meant to be supplemented by another, specifically 261 million pounds coming from industry. And that has led to kind of a series of cluster projects that have been led by kind of a local government, local enterprise partnerships, for example, and also has led to competition for this 170 million that's on the table. And you see these 6 major projects put together and put forward by many large industries. The Humber project, for example, is led by Equinor. The Net Zero Teesside project is led by BP, and so on. And this kind of gives you a map of where these projects will be. There are still some challenges just in the last minute or so that I think this kind of new approach faces. First of all, certain of the kind of most heavily emitting industries are in a decline. Some would say sort of terminal decline. So the steel industry in particular, which had been, say, the key project originally was the key project in the Teesside cluster, has, basically gone out of business, went out of business several times actually, and now they've kind of turned off that plant. The steel plant in South Wales, Tata plant, is also in dire straits. If you think of it in political terms, the number of steel workers in the country has declined precipitously over the course of the 70s and 80s to the point that it's really quite small workforce. On the other side, there are some industries, notably the chemicals industry, that is still doing well, and so that leaves us maybe with a couple of final questions. Government needs to put forward a set of business models that actually will allow companies to take their projects and bring it to some sort of final investment decision. But there are some, I think, lingering questions whether industry is genuinely committed. These are trade exposed sectors. It's very easy for the chemicals industry, INEOS most notably, to threaten quite legitimately to move if they're not happy with the outcomes. It's relatively easy for government to commit some hundreds of millions of pounds, but the sort of numbers that you will be needing to get, say, 4 industrial clusters off the ground will run into many billions, and so that's, I think, a big challenge. I think the support for this in terms of the broader society is untested. You don't have the same level of opposition that you do have in a number of European countries, but there are green groups, other advocates who are skeptical or even slightly hostile to many of these solutions. And then finally, if this will go through, if this will increase prices on plastics and other construction and so on, there is a question of the willingness of consumers to pay higher prices. Okay, that's it for me. Thank you.
Thank you very much, David. That was perfectly to time as well. Thanks for an interesting presentation. We've got a few questions coming into the Q&A already, so I'll just jump straight in here with the first one, which is, what are your thoughts on the recently approved coal mine in Cumbria, approved by the Cumbria County Council, and which the UK government hasn't stepped in to prevent? What are the pros and cons, and does this undermine our negotiation position for COP26?
Yeah, there are a few questions in there. One point that the advocates of this coal mine raise is that it's not for electricity generation, but it's for steel. I think one of the big problems that we have, of course, is that we are the fact that our steel industry is in decline doesn't mean that we're not using steel. It just means that we're importing steel from places like China, and the carbon intensity of their steel is higher than the carbon intensity of our steel would be. So there's a question in practice as to whether stopping this coal mine, stopping steel from manufacturing from going ahead in the UK will solve the problem. But that is different from the point about the UK's posture or UK's position with regard to COP26. So I think there are reasons to believe that project might end up getting knocked down. Not necessarily because that will mean we'll be doing anything about our steel consumption, but just because the optics of it aren't great.
Okay, thank you. I'm just going down the list here. The next question that we've got is, has there been consideration to the energy requirements of carbon capture compared to the total amount of energy available in a low carbon future? An energy transition to low/no carbon will lower the total energy capacity due to the low energy density of sustainable energy resources. How can we reconcile using energy for carbon capture, utilization and storage with increased demand on the national grid?
So I'm not sure I totally understand that question, but I think it is true that one of the advantages of carbon capture and storage is that you are able to apply it to more energy dense fuels. And so that is exactly why the Committee on Climate Change and others would argue that you can debate the necessity of CCS in power, but with regard to industry, where you do need kind of that kind of a higher grade heat, higher grade energy, that's why CCS is kind of an absolute or an absolute necessity, but it's seen as desirable if you want to continue operating as these energy intensive industries currently do.
Okay, thank you. A few questions here from David Newbury. Would a decent carbon price make CCS profitable? And can you comment on why it is illegal to build CCS in Germany?
So it's not illegal. A certain state, certain lender like Schleswig-Holstein have banned storage of CO2 underground. It is also true that if Germany were to take net zero seriously, and Germany being the largest industrial power in Europe, it would need to do something about its industrial sector emissions. And so therefore, I mean, Chancellor Merkel and others have very tentatively tried to broach bringing CCS back up onto the agenda. But it has been taken off to date, and I think that is a big question. It might also indicate kind of the seriousness of the German commitment to net zero, because I don't think they're going to get out of their heavy industry anytime soon. With regard to the carbon price, well, I mean, I think that is very much varies from sector to sector. You would need quite a significant price, but the biggest problem, as I said, is because of the trade exposure of these sectors. that these firms really aren't willing to tolerate any sort of additional costs, and so they sort of can threaten to leave, and so it will end up needing to come through subsidies rather than prices. I think that if you are to decarbonize industry.
Okay, thank you very much, David. Unfortunately, we have to move on to the next speaker, and we won't be able to have time to do all the questions today. But as I said in the introduction, we will collate all these questions that have come in and get answers from David, hopefully by in writing, and then we can circulate them around all attendees after the event. So
okay, I can also try and type my answers here as well. Can I do that?
Oh yeah, if you want to type answers straight into the Q&A, that would also be great. Yeah, thanks a lot. Okay, so could I ask you to stop sharing your screen, and then we can move on to the next speaker, which is Sam Stranks from Physics and Chemical Engineering and Biotechnology. So Sam, would you feel free to share your screen?
I think I can't share yet. David, if you could unshare, then.
Yes. There we go. I think you should be able to share now.
Okay, can you see the slides?
Yeah, we can.
Excellent. Well, thanks very much, Eric, and thank you very much for the invitation. Looks like a fantastic symposium, a series of symposia over the next few weeks. So I'm going to talk today about our work on new PV technologies in particular. I'll touch a bit on lighting towards the end, but just in the interest of time, I'll focus it around PV in particular. And so one thing that is very exciting is that solar PV deployment is growing very, very rapidly, very fast. And this plot shows that quite nicely, that this is a plot of the cumulative solar capacity, deployed capacity over the years. And you can see in the dashed line there, that's these are the projections made by the International Energy Agency. And you can see every year consistently for the last decade or so, the IEA has under-predicted how much solar will be deployed. So in the black dots there, that's the actual observed deployed amount. So this is exciting. There's a lot of solar PV coming online. This has been driven predominantly by cost reductions. And in fact, PV module prices have dropped by a factor of 100 since 1980 and almost a factor of 10 since 2010, so even over the last decade. And this is, again, very, very exciting for what we need to be doing, putting solar and deploying solar in the field. And most of this cost reduction is from economies of scale, so materials and manufacturing costs have come down, and also from power conversion efficiency gains, so R&D factors that have been improving over the decades. So crystalline silicon is the technology that is the market dominant technology. It's 95% of panels deployed are made of crystalline silicon. It's a very good technology. It's taken us to where we are now, and it will take us forward a long way. But it's not going to get us all the way there. So we're at something like a terawatt now, or approaching a terawatt of solar. We need on the order of 10 to even 20 terawatts of solar, and this existing technology won't get us all the way there. And so there's two reasons for that. One is that the costs are starting to plateau, and this is particularly because in a solar system you have the module, so that's the actual panel itself and the cost of the panel, but then there's also, so that's the module cost there. But then there's all the balance of systems costs. So these are this is the installation, the wiring, the inverters, and all the other costs. And so this plot showing rooftop systems in Germany, you can see that the module cost has really come down, and in fact, it's continued to come down. And that will approach something like 20 cents per watt for the module. But these balance of systems costs here in blue, these are plateauing. They're much harder to make inroads in. And so actually PV systems now, and in future will be dominated by these balance of systems costs. And the other aspect is that to make silicon cells, we need to heat them to very high temperature. The processing is very expensive. And so this means there's a lot of capex to build factories. It means we can't build factories fast enough, and therefore we can't deploy PV fast enough. So this is limiting how much we can get out there, and also limits applications because of the high temperature processing. So really, going forward, we need other solutions that will have higher efficiency, and therefore reduce costs. And so just as an example of that, the balance of systems costs, if we increase the efficiency, that will bring down the balance of systems costs because for a given PV system, we'll be producing more power. So this brings us to the materials that, one of the material families that we work with are these halide perovskites, and in many ways it can be thought of as a new world of semiconductors in that we can process them very inexpensively and somewhat crudely, but they can perform very, very well. And this goes against the sort of the dogma that a semiconductor should be perfect, it should be crystalline, highly crystalline and perfect with no defects. And so this is a somewhat step change in that way of thinking. And so this is how we process them. So typically we process them with solution. We have inks that are made that we dissolve our precursors in, and we spin coat them or cast them down with solution processing that make these yellow films here, and then we gently heat them to 100 Celsius, so they form these really highly crystalline PV materials, which you can see here. And so this is very low temperature for semiconductor processing, 100 Celsius. So this, and I'll show in a few minutes why this can lead to some interesting applications and also cost reductions. One thing it can enable is very high throughput manufacturing of these cells. So you can manufacture them on plastics or on foils, and this allows things like roll-to-roll processing, where you can think about printing them like newsprint and really increasing the throughput. You can customize them, so we can change, for example, they take the ABX3 crystal structure, so we can tune the components and change things like the band gap, which is basically what color the material absorbs. So changing from something that's iodide through to bromide, you can see can really change the absorption color and the emission color. This plot shows probably why they're creating a lot of excitement in particularly in the PV community. This is showing the power conversion efficiencies of silicon and perovskite technologies over the decades, and you can see silicon has slowly progressed, and it's now at about 27%, whereas the perovskites over the last decade has really rapidly shot up, and it's now at 25.5%. And as of about a month ago, this new point on the chart, and in fact, it will very likely approach or even overtake silicon in the near future. Just as a note, the efficiency limit of solar cells is roughly, at least of a single junction solar cells, roughly 30%. So they're starting to get towards the saturated limits for where they can get to. And particularly for silicon, that limit is about 28%, in fact. And so if we think about processing them on plastics and on foils, it also enables lightweight solar applications. So really high power lightweight solar, which leads to things that, or applications that really need high watts per kilogram. And so this enables a number of new applications for solar. So space solar and high altitude aerial vehicles, which are becoming a lot more popular for communication applications, and that market's going to grow quite sizably. In particular, also for rooftop solar, that a lightweight flexible panel actually reduces the installation costs quite significantly, and also boosting the range of electric vehicles. So high cost per watt is high watts per kilogram is very important there, and so you can put something that will add extra power without adding extra weight. And actually, I'm one of the co-founders of Swift Solar, who are commercializing some of these lightweight, high performance aspects. And really, what I see as one of the biggest potentials for perovskites is for the efficiency improvements. And this is using things like what's called a tandem PV, a tandem solar cell approach, where you can actually layer two of these cells together. The top cell harvests the bluer wavelengths and the higher energy wavelengths, and then the redder wavelengths pass through and are harvested by the lower cell. And these cells are coupled together in series, and the net combination of that can take us beyond that 30% limit. And in fact, a practical limit for a perovskite tandem like this is something at around 35%. And this is actually a huge breakthrough in terms of efficiency. And when you think about the levelized cost of electricity over the lifetime of the panel, there's a lot more energy produced over that time. And that also reduces the energy payback time because of the manufacturing temperatures and processes being a lot more energy efficient, and also greenhouse gas factors coming down. One of the first commercial products is most likely going to be a tandem configuration with on top of silicon cells. So this is actually taking a perovskite cell and processing on top of the existing technology. And this is something that the company Oxford PV are pioneering. And so here they can leverage a lot of the existing technology and infrastructure and even manufacturing to do this. So you're essentially boosting the current, the efficiency of the current technology. And this actually, even just at the end of last year, hit over 29%. So even in terms of performance, that's already beyond silicon and even beyond the limit that silicon alone could reach. In terms of commercialization, so it's very likely this will be the year of four perovskites, and this is the first products will be coming out. In fact, the second quarter of this year, Oxford PV and also Microquanta Semiconductor both have planned products coming out. They both have manufacturing lines on the order of 200 megawatts. The Oxford PV one's based in Brandenburg in Germany. So that's very exciting, and it's an exciting time for the technology. And there are various other companies as well progressing in terms of investment and also building manufacturing lines. But of course, there are challenges remaining, and this is what I'll focus on for just the last part of the talk, really what we're working on around these issues, and really what's limiting them from really making at least disruptive impact on PV. So how do we take efficiencies to and above the traditional limits? How do we scale up to larger area cells and modules? A lot of the work's been done on relatively small kind of 1-inch square cells or mini modules, so scaling them up to full panel size is a challenge. And also, how do we make the panel last for 30 years, which is the current benchmark for that silicon has set. So who are we? This is our group, what we do. So we're based in chemical engineering, biotechnology, and also within the optoelectronics group in the Cavendish. This is what we looked like, at least in October 2019. This is what we look like now, which is what many of us look like at the moment. We're squares on a screen. But we're quite an eclectic mix of, we're very interdisciplinary. We've sort of moved from physics and chemistry through to engineering and device processing. And one of the real things that drives a lot of what we do is optical spectroscopy, where we use fast lasers to look at to replicate sunlight and see how long charges take to recombine, or if they're trapping, or how long does it take to collect them. And that can tell us a lot about power losses in solar cells. And one particular technique we use is looking at luminescence. So actually look at light coming out of the solar cell to probe power losses. It's somewhat counterintuitive to say that looking at light coming out of a solar cell is a good thing to do. But actually, if we don't collect the carriers, when we shine light on there, then the carriers that we excite have to recombine, and then they themselves emit light. And so they can either do that, or they could trap into defects and other unwanted sites in the cell, and this will quench the luminescence. So this luminescence gives us a good measure of trap states and how good the materials is performing. And so some examples of that, so we're looking at these in microscopes and looking at luminescence on the microscale. This is a confocal photoluminescence map of a perovskite film. You can see these grain structures, they're kind of mosaic grains, and this is on the scale, this is a 2 micron scale bar. And you can see that the photoluminescence, the color here, some grains are very bright and luminescent, so they're very well performing, but some of these grains are actually very poorly performing and quite defective. And so we want to understand why they're defective and how we could get rid of that. And so we've been trying to understand exactly what causes these trap states. And this here is a photoluminescence map again. So looking at the light coming out of a cell in the color from this black to yellow color plot. And then these blue spots are actually trap states. So these are they're clusters of traps that are sites that trap these carriers in the cells. We're probing these using photo emission microscopy. And you can see that they sit in the dark spots of the luminescence, so that where there's poor luminescence, there's these trap states, and that tells us these trap states are problematic for performance. And so we've been working with a collaboration with Paul Midgley and Kate Ducati in materials to understand exactly why these trap states form and where they form. And it turns out they form in little clusters that sit at certain grain boundaries. So this is in blue here. This is one of the in that middle diagram. This is one of the trap clusters, and it turns out they form only at specific grain boundaries, and it's grains between a distorted grain. So we can look at the electron diffraction pattern of this grain and see it's distorted compared to this grain, which is more pristine. So these junctions are the problematic cause of these power losses. And so we've been working with the team in Okinawa, so Keshav Dani, a collaborator, and this is where they can optically excite the sample. And this is the time after the excitation. And what you're seeing here in the black, these are actually carriers trapping in real time in these nanoscale trap clusters. So it's a very, very cool technique to visualize these trapping processes. I'll let that play. And so now we've got a bit more understanding about what these traps are and where they're forming. So we're now looking at different things that we can do, so additives and post-treatments to be able to get rid of these traps and therefore clean up the luminescence. And so this is a map looking at, you can see many dark grains and it's quite heterogeneous, and we've treated it and you can see a much better film in terms of luminescence homogeneity, but also in terms of the device performance from it. A couple of other things we're doing just to finish. We're looking at particularly again at light and how we can make every photon count. And one particular interesting thing is that when we absorb a photon and those carriers aren't collected, we emit another photon, and that photon can be reabsorbed somewhere else. And so this is something that's called photon recycling. In fact, that can happen many times in the cell before you collect it. And one thing Alan Bowman's been looking at in particular is if you have emission from, in a tandem, this is a tandem cell, you have emission from the top cell, you can actually reabsorb that light in the bottom cell. And so this is called light coupling or luminescent coupling. And this actually has a very important feedback mechanism, or gives a very important feedback mechanism to the cell, because usually we have to have a very stringent current matching conditions between these cells to make them work. But this light gives an additional pathway to feedback. And so this actually opens up a lot of the material constraints actually get relaxed. The material constraints on these two, on the top cell and the bottom cell, get quite relaxed. And so this is just an example here on the right, looking at different thicknesses of the low gap, the top cell and the bottom cell, and the peak efficiency. You can see that the dashed line represents the peak efficiency region. You can see that's quite tight if you don't consider light coupling. But when we start to consider the light coupling, you can see that opens up really quite significantly. And so this actually allows us to design the cell in a much more flexible way. We've also been doing work of scaling up the devices, and this is some work that Yuxian and Miguel have been doing in actually the Royce ambient cluster in the Maxwell building. This is looking at vapor deposition of the halide perovskites instead of solution, and this gives us flexibility in terms of processing on different materials. With solution, that you have some problems with washing away the layer underneath. In vapor, you don't have these problems. And you can see you can also form very nice large area films as well. We've also been looking at how they can be used for space applications, and we see that that actually these materials are very radiation tolerant. So this is looking at proton radiation of cells to be put in space. And you can see that the perovskite under proton radiation is a very, very stable, and this is actually a dose equivalent to 50 years in the ISS orbit. Whereas if you compare that to a silicon tandem, that dies away very quickly. And this comes back to this defect tolerance that we have in the perovskites, that even with bombardment, you don't create defects that are problematic. In fact, recently we've been looking at the perovskite tandems, and you can see that they are extremely stable, even up to very, very high doses. And that's even much more than the 3.5 tandems, which are actually currently commercial in space. And
I'm going to have to stop you.
Yeah, no problem. So I just wanted to show with stability that this is the final challenge, that stability is one of the big challenges to tackle, and there has been a lot of progress made recently. We think a lot of this relates to these trap states as well. So with that, I'll wrap up, and thank you very much. Thanks, Eric.
Thanks very much, Sam. That's great, and a great overview of all the work you guys are doing. We'll quickly go through a few of the questions that have come up in the Q&A. There's a question here saying, why do the current PV cells have such a low efficiency, and where is most of the energy lost?
Yeah. So I said about the 30%, limit. So that's actually a thermodynamic limit. because we can't, so we have a fixed band gap that we're absorbing, and so we can't harvest energy, photons with energy below that band gap. Those energies, those photons pass through and aren't absorbed. Any photon above that band gap, we absorb, and then a lot of that energy is lost to heat when it relaxes to the band edge. So actually that sets up a thermodynamic constraint on cells. There's also the modules in the field. There's also other losses as well that actually bring them down to more like 20% efficiency, just because you have electronic losses as well at large area.
Okay, thank you. Another question here: how are companies facing and resolving with the stability and toxicity challenges? So,
yes, yeah. So stability challenges. So maybe just to go back to this. Some of the more recent compositions are much more stable, and this is replacing some of the problematic components, such as methyl ammonium, which is an organic cation that was quite volatile. That's been replaced with other cations such as formamidinium, and these compositions are much more stable under illumination and under constant operation. So this is actually a plot showing a few thousand hours at elevated temperature, which is a standard industry standard test. And it's passing that. So these, in terms of stability, that's looking very good. In terms of toxicity, so yes, I mean, these materials do contain lead. Because the absorber is extremely thin, there's actually a very small amount of lead in total. In fact, it's actually less than in silicon panels, which lead's used in solder. But what it really means is that packaging is going to be important. So making sure these cells are well packaged, and also even recycling models are brought in to make sure the end of life is also considered. But that is a surmountable challenge.
Okay, so I think that kind of also answers the question here about the afterlife of solar panels and the environmental impact. And maybe finally then the question here: have you got any thoughts on Tesla's solar roof and whether it's yeah, I mean, it's very interesting. I mean, certainly the lightweight PV, this is where it can be very very useful, and it's certainly a market that will grow as well. It's something that we've started to engage a bit with them as well on that through Swift. Okay, great. I think we'll have to leave it there to carry on, but if there are any other questions for Sam in the Q&A, feel free to type the answers out there in the Q&A, Sam, and then we can also share the answers later.
Yeah, happy to answer some. Thank you very much.
Great, thanks a lot. Okay, so we'll move on to our next speaker now, is Dr. Siân Dutton from the Department of Physics, who will be speaking on magnetism as a probe of batteries. So over to you, Siân.
Okay, all right, thank you very much for the introduction, and thank you very much for this the invitation to speak here today. So today I'm going to talk about some of our work, recent work looking at magnetism as a way to probe changes in battery materials. And this really links with wider research within my group, where we're interested both in sort of materials for rechargeable batteries, but also looking at magnetocalorics and novel magnets. And this is allows us to link these two fields of research together. So I've got here a schematic of a rechargeable battery, and here we have two electrodes. And as we charge and discharge, we move sodium ions between them. And to ensure that we have charge balance, our electrons are driven through our external circuit. And then as we do this, we change the amount of sodium in our transition metal oxide, here sodium cobalt oxide, and this enables us to store the charge. And if we look at this from a sort of a condensed matter physics perspective, what we find is actually sodium cobalt oxide is not only of interest because it can be used to store energy, but also there are a whole range of other functionalities which arise from the varying sodium composition. So as I've already said, we can use this in a sodium-ion battery, but we can also use it for some compositions as a thermoelectric. So this is a way to take a temperature gradient and use it to generate electricity. And this arises from the fact that in some of these compositions you have a large amount of sodium disorder, which means that you have very, for an oxide at least, very attractive figures of merits for a thermoelectric. On other compositions, you get very subtle and very beautiful vacancy orderings, which give rise to a whole range of other electronic effects. And also, if you have the right sodium composition and a little bit of water, you get a material that is superconducting at low temperatures. So what we asked ourselves is, can we use some of these effects which give rise to functionality in these sodium deficient materials to understand and explore the properties in a battery? So if we think about this in a little bit more detail, if we go to from our sodium to our lithium containing compound, we start with a material on our electrode which is non-magnetic. It contains cobalt with no unpaired electrons. But as we remove lithium, we generate we oxidize some of our cobalt from 3+ to 4+, generating unpaired electrons and a magnetic moment. So this is something that has actually been studied in samples prepared in the lab. And what you can see here is that as you change the amount of lithium in the material, you get sort of a systematic change in the magnetic susceptibility. So this is just telling us something about the number of unpaired electrons, so the amount of cobalt 4+ or lithium we have in our material. And it's easier to see if you plot this in an inverse way, where the number of where the gradient is going to tell us something about the number of unpaired electrons. We can also determine the strength of the magnetic interactions, and that in other systems we can use to infer information about how the magnetic ions are arranged in space. So I've shown you this example on materials which have been prepared directly in the lab with known lithium compositions. Can we also do this in battery type materials? So the first example I'm going to give you is actually not in a lithium ion battery, but in a magnesium ion battery. These are attractive, though much less well-developed battery technologies, where you replace your monovalent lithium ions with magnesium 2+. And the advantage of this is that for every magnesium you move through your battery, you move 2 electrons through your external circuit, so you can potentially increase your capacity. And the material system we were studying was this magnesium manganese pyroborate. But the issues here is that whilst this is very attractive, it's actually very difficult to demonstrate that you can change the oxidation state of your transition metal by a sufficient amount to remove all the magnesium. So and this is sort of just commented in this paper here. So our electrochemistry looked like we were removing all of our magnesium on the first charge. So we wanted to confirm this through some other experiments. So what we did is we went away and we measured the magnetic susceptibility and looked at the size of the moment as a function of state of charge. And here what we see is that we have results which are consistent with our manganese being oxidized from manganese 2+ in our fully magnesiated material to manganese 4+ when we think we've removed all the magnesium. And this is a rare example of a 2-electron redox in a magnesium ion system. So just in case you don't believe me, we can then go away and we can verify this using X-ray absorption spectroscopy, and we see results which are broadly consistent. So my second example of this is using a magnetism as a route to study structural disorder. And this is a different type of lithium-ion battery material, a so-called disordered rock salt. So this has a different structure where you have 3 different cations, lithium plus, niobium 5+, and manganese, which are all disordered within the crystal structure. And what's interesting about these materials is that they have an excess capacity associated with changes in the oxygen oxidation state, not just the transition metal. And what we find is that we can make these materials with different degrees of disorder in the crystal structure, and that the capacity retention we observe is highly varied depending on whether we have something which is depending on the degree of disorder we have in our material. So we can study this disorder and we can find out more about it. using diffraction. So this is just showing our ordered and our disordered material. You can see in our disordered material, if you look very closely, that we still have some features which suggest we have very local ordering. But we can ascribe this ordered phase due to the lithium localizing primarily on one site, with the residual of the lithium and the niobium and the manganese on the other. And so because of these changes, what we find, or what we can sort of conclude, is that we have different lithium-ion pathways, which is what gives rise to the differences in the capacity retention. So we can also look at the nature of this ordering, particularly the relationship between the magnetic manganese ions using magnetic measurements. And there, what we find is that we don't have differences in the inverse magnetic susceptibility, so the size of the spin. These have nominally the same composition, so we wouldn't expect there to be differences in the gradient. But instead, what we see is that we have very different values for the Curie-Weiss temperature. And this is telling us about the nature of the magnetic interactions. And we can sort of roughly correlate this to the number of manganese with 90-degree bond angles versus 180-degree bond angles, because we would expect them to have different strengths. It's a little bit more complicated than this, but this is consistent with our structural model. And we also see this in some NMR, which shows us similar results. So having sort of demonstrated this on sort of two sort of new, sort of more less well-developed materials, we also wanted to look at a more commercially relevant system. And this is this lithium nickel manganese cobalt oxide, or NMC. And this is a similar type material to the lithium cobalt oxide, which I discussed right at the beginning. So this is an ordered rock salt where we have alternating layers of lithium and transition metal. And we have a mixture of nickel, manganese, and cobalt in our transition metal layers. And this has a number of advantages, which gives us better capacity and stability. However, it does come with some disadvantages. So this is just sort of showing how this sits within the parent materials of the cobalt, nickel, and manganese. And the composition we're studying is over here, and it's quite close to lithium nickel oxide. So when we are thinking about the magnetic properties, we're going to be comparing this to the lithium nickel oxide, because we have 80% nickel in our material. So it turns out that lithium nickel oxide has been extensively studied, but that there are lots of contradictory reports out there about it. So this material is of interest because it has spin half ions on a triangular lattice, which potentially means that it's a candidate for very exotic physical states. But what's important from our perspective is that actually it's very difficult to make this. And instead, what you find is that it's prone to large or to very small amounts of osteochrometry, which have a very dramatic effect on the magnetic interactions. So we should be very sensitive to small amounts of changes in the lithium content, but also in site disorder between the lithium and the transition metal sites. And this potentially will have an impact on the cycling performance. So just to summarize, when we're discussing this, we would expect our 811 to inherit the problems of sample dependence associated with lithium nickel oxide. And so to understand these things, and the magnetic properties, we're going to need to characterize the stoichiometry, so the composition, but also the degree of site disorder. And that when we're doing this, we need to also take into account that we have a large number of different ions within our transition metal layer. So this is a very complex system. So when we were studying these materials, we had commercial samples from a supplier called Targray. And so these are nominally the same composition. And what we find is that we see very different magnetic properties depending on whether we're measuring sample 1 or sample 2. Most significantly, they have different sizes of the magnitude of the magnetic susceptibility is different at low temperatures, but also when we collect the measurement in different ways, we get a divergence in sample 2, whereas we don't in sample 1. And we can characterize all these properties, and these are summarized in the table. There are some things which are similar, and then there are other things like this divergence, where we have one where it's at 8 Kelvin and another one where it's at 122. So this is a large difference. And we can also use a different route to get a composition out. And what we find is that within error, these are similar. So if we want to understand this fully, we have to go away and collect more measurements. So we can do this by using scattering as well. And we apply a number of different constraints, which I'm not going to go into here. But what this allows us to do is ensure that our analysis and the composition we get out is consistent across all the data sets that we've collected. And here what we find is that we have very different values, both in the lithium deficiency X by an order of magnitude, but also in the ratio of nickel to manganese within our material. And we ascribe this to changes in the magnetic properties. This is giving rise to changes in the magnetic properties. So that's all very nice, but what can we learn about how this material cycles from our magnetism? So to do this, we can make magnetic measurements as a function of state of charge. This is just the first charge, and we can evaluate the temperatures and the effective moments we observe in our materials. So what's important here is that we can use this to track what our redox active species are and understand more about how the NMC is operating. So what we see is as we charge our sample, we get a reduction in the magnetic moment, which is consistent with oxidation of our nickel, and that we don't see any evidence for oxidation of cobalt 4+. And this is quite important because this is something that's sort of contested, and oxidation of cobalt 4+ might lead to oxygen evolution, which is something we want to avoid in our batteries. So I think my time is coming to an end, so I'd just like to briefly conclude. I hope I've shown you that we can use these magnetic measurements to provide a way to explore the structure and state of charge in battery materials, and that we can use these to evaluate more complex systems which are sort of more relevant to the batteries which are being sort of commercialized today. Before I end, I'd just like to acknowledge my group who've really done all the work. This is us last year when we were sort of still able to meet in person. The results I've shown you today are primarily from the PhD thesis of Mike Jones and Hugh Glass, and from Torrente and Mukherjee. And finally, I'd just like to thank you for your attention.
Thank you very much, Siân. That was a great presentation. Can I ask you to stop sharing your screen as well? Great, thanks. Okay, so we have a few questions for you here in the Q&A come up. So the first one here is, how do your magnetic systems compare to single molecule magnet technologies, and do they have a place in battery technology?
Okay, so I must admit I'm not an expert on single molecule magnet technologies, so I can't comment too much on that. I mean, what we're doing here is we're using the changes in the magnetism as a way of probing what's happening in the material. So it may be that if you had a single molecule magnet where you change the magnetic properties in some way on some sort of degradation process, perhaps associated with a change in the electrolyte, then it may be that would be a way to probe that in situ.
Okay, thank you. And another one here, which is on solid state batteries and what needs to be done to make them commercially competitive with current lithium ion battery technology. Okay,
so in a solid state battery, you replace your liquid electrolyte with a solid electrolyte, and this has a large number of advantages: safety, potentially higher energy densities. But they are challenging to manufacture, and there are issues with them sort of cycling over the long term. I definitely see them having a place, but I think that there are challenges which need to be overcome before they can be fully part of that. And that's the case for lots of these developing battery technologies.
Okay, thank you. And then, unless there are any other questions from the attendees, I might put a question in there myself as well. So you used, if I understood correctly, you said that these disordered structures were leading to higher capacity in your findings. So do you think there is a future for that to be developed, to be used in more commercially used batteries, for instance, with this disordered structure?
So it depends a little bit on the type of ordering you get as to whether a disorder or ordering is beneficial. In the case of the system we're looking at, it's not beneficial. I think these materials are potentially are very exciting because they have this additional capacity from the oxygen redox, but there is work to be done on sort of retaining this capacity retention and sort of being able to charge quickly enough.
Okay, right. Thank you very much. I think in that case we'll carry on to the next speaker. So thank you, Siân, for your presentation and your Q&A, and then we'll move on now to Dr. Laura Torrente from biotechnology, who will be speaking on power to X to power, ammonia as X factor. So Laura, over to you.
I'm trying to start. Here we are. Okay, well, thank you very much for giving us the opportunity to present our research and our vision on ammonia. So let me start by putting our research into context. So one of the good things about fossil fuels is that they are extremely versatile. So over the last century, we've been able to meet our demands on electricity, on transport, on heating, on processes by using fossil fuels. And the way that we do that is just by simply burning them, and then we produce CO2, and we know all the issues associated to that. So over the last couple of decades, we have had a disruption by renewable energy. And now the UK can supply a good fraction of the electricity needs using renewable energy, and that includes biomass. But the problem with renewable energy is that it's intermittent, is unpredictable, is isolated geographically, and it has a very is not as versatile as fossil fuels. So what we need is a buffer. We need a buffer, and the main player here is hydrogen. So we can use hydrogen to produce the electricity whenever we need it, and thanks to that, I think that we have also had an entry into the transport sector using the batteries. Okay, but hydrogen has some issues. The first one is associated to safety. So it is a flammable gas. And the second one is associated to storage of hydrogen. So the US Department of Energy establishes the targets for the feasible applications of hydrogen. And this is a moving target, so it moves between 5.5 to 7.5% by weight. And this graph is an old one, but it represents still, excuse me, the situation at the moment. So this is the way that we can store hydrogen at the moment using physical means. And there is a step change here, and it's because of the discovery of the metal organic frameworks and microporous materials. But still we have issues about what are the conditions that we need to release that hydrogen, and what is the rate at which we release that hydrogen. So as I say, these are physical solutions. And what I'm going to present today is an alternative on how we can store hydrogen on chemical bonds. And in this context, ammonia is unique. It's unique because it's the only carbon-free energy vector. And it can store a large amount of hydrogen, around 17.6% by weight. So well above of these targets. Okay, so this is the way that we can see the role of ammonia as an energy vector. So we can definitely store hydrogen, and ammonia is very versatile. So we can replace, in theory, fossil fuels. We can use fuel cells, we can still combust it to meet the different demands. But what our group is focusing now is how we can couple the production of renewable energy with the production of ammonia, so we can store it. So the way that ammonia stores energy is very, very similar to the way that methane stores energy. So methane has 4 carbon-hydrogen bonds, and it's by breaking these bonds that you release the energy. So ammonia has 3 nitrogen-hydrogen bonds, and it's just by breaking them that you release the energy. So it's exactly the same concept. So we can say that ammonia is kind of a decarbonized methane. And the difference between these two is that methane has this carbon atom in the center, so it produces CO2. Ammonia will produce only nitrogen as a byproduct. Okay. In terms of energy density, well, ammonia is a gas at room temperature and atmospheric pressure, but we only need 10 bars of pressure if we want to liquefy that. And if we compare that to hydrogen, we will need 350 or 700 bars of pressure to liquefy hydrogen. So ammonia contains more hydrogen than pure liquefied hydrogen in terms of volume and in terms of mass. Okay. In terms of safety, well, ammonia has a flammability range much narrow, between 16 to 25%, than hydrogen, which is 4 to 75%. We also need to acknowledge that ammonia is toxic and is corrosive, but it is very easy to detect it by smell, okay? And at concentrations well below of concentrations that are harmful for us. It's not a greenhouse gas, but it can be decomposed by bacteria in the soil and produce NOxes. So if we are going to use ammonia as a carbon-free energy vector, we need to be sure that we are not going to release it to the environment and we don't produce a bigger problem than the one that we actually have. So we produce at the moment ammonia in large scales. We produce around 175 million tons of ammonia because we use it as fertilizers. And then there is a very well-established and mature transport infrastructure. So this is a map of how we ship ammonia at the moment and how the main ports around the world know how to handle ammonia. In some countries, for example, United States and Russia, there are also pipes to transport ammonia. And in the United States especially, there are over 3 miles or 3,000 miles of pipes to transport ammonia between different states. So we know how to handle this chemical. Okay, how can we produce ammonia? How can we convert our renewable energy to ammonia? Well, the first thing that we need to see is how we produce it at the moment, okay? And it's through the Haber-Bosch process. This is probably the oldest chemical process in the world, and everybody around the screen who has an A-levels in chemistry knows or has known at some point about this process. So very, very famous process. So it can be broken into 2 steps. The first one is about the production of hydrogen. So in this case, we use natural gas to produce hydrogen, and here is where our CO2 is coming from. Okay, so it's coming for the production of hydrogen, and is producing around 1 to 2% of all the CO2 carbon emissions. So it's a huge amount. It's highly energy intensive. And the second step is the ammonia synthesis itself. So here is where we combine hydrogen and nitrogen to produce ammonia. And this is called the Haber-Bosch loop. And the reason is because every time that these reactants go through the reactor, they are converted only in a tiny little fraction. Okay, and then they need to go in circles in this loop until you get very high levels of conversion. I said before that this is one of the oldest chemical processes and is also one of the most optimized chemical processes in the world. But in our opinion, this is a false optimization. So this is an optimization that is based on the use of all the excess heat that you produce in the first step when you are burning natural gas to produce steam to drive the second process. Okay, there is also what is called blue ammonia, and is exactly the same process but capturing the CO2. What we want to do is green ammonia. So what we want is to completely replace the use of methane or any other fossil fuels by using water splitting. And this is where our renewable energy can be stored. So we can produce hydrogen, and then we can keep the second step in exactly the same manner. If we do so, we will decrease the CO2 emissions by at least 75%. Okay, but we need a completely new optimization of this process. We need to be very careful about how we do this. I have to say that this is not a new idea. So this was already suggested in the 60s or 70s, but it never took off because fossil fuels were very cheap at that point, and there were not any environmental restrictions there. Okay, so the technology is feasible, so it's ready, but the production of green ammonia is less efficient than the brown ammonia. So what my group is doing is trying to understand the process, trying to do techno-economic analysis to see where we have opportunities to increase this efficiency. So in this graph, I show the current method, the methane-driven process, with the green ammonia. So the red palette is representing the energy losses for hydrogen production. Okay, so if we replace that with electrolysis, you can see that electrolysis at the moment is not efficient. And that is the current limitation that we have for the production of green ammonia. So I'm encouraging everybody around Cambridge who is doing research in this area to keep going, because we really need to produce green hydrogen. And then in terms of the ammonia production, well, there are also quite big losses of energy here, and we need to redefine the system. What else is important to know? Well, renewable energy is, as I say at the beginning, geographically isolated and is intermittent. So we won't be able to run a process as we know it at the moment. So what we know is to redefine completely the Haber-Bosch process. We need to question the way that we are doing this kind of chemistry. And we need to have more efficient, more distributed, and more agile systems. By efficient, I am referring mainly to electrolysis, as I say. By distributed, I think that we need to link the production of renewable energy to the production of ammonia. So we need to escape from the grid system. And in terms of agile, well, the process at the moment is running at very high temperatures and very high pressures. And we need to do it better. We need to think about new catalysts. We need to think about new systems to make it very agile, so easy to respond to the fluctuations of the renewable energy. And that's where we are focusing at the moment in the group. And Collin Smith is going to present later on how we are achieving this in the lab. Okay, the second thing is ammonia to power. So once that we have the ammonia, how can we convert it to power? So I say that ammonia, one of the good things, one of the many good things that it has is that it's very flexible. It's very versatile. So we can crack ammonia to release the hydrogen and then link it to a PEM fuel cell. And this is the technology that has the highest maturity degree at the moment. But we still need to do quite a lot of work in terms of releasing the hydrogen at lower temperatures and have full conversion so we don't poison the fuel cells. There are other strategies. One is to use a direct ammonia fuel cell. Quite a lot of groups around the world trying to develop this. It's still in early stages, but very, very promising. And the other thing that we can do is to directly combust ammonia. And as I say, if we do it efficiently, we will produce only nitrogen as byproduct. But we need to be very careful with the NOx emissions. So the combustion is not as good as if you combust, for example, fossil fuels. So one strategy around that is to link the first point with the third one. So if we crack a little bit ammonia, we can have ammonia hydrogen mixtures that burn much better and reduce the NOx emissions. But my group is focusing at the moment on the cracking of ammonia. How can we release that hydrogen? So all the research, most of the research in this area is done at high temperatures, and there are reasons behind that. And the reasons are because people were trying to find a good catalyst for the Haber-Bosch process. And they were not interested in cracking ammonia for hydrogen production necessarily. But now we are shifting the target into too low temperatures. So this is what we have so far achieved in the group. So we have a good catalyst that can now release the hydrogen at relatively low temperatures, around 180 degrees. There is still a scope for improvement, but we are proving that this is feasible. It's a ruthenium-based catalyst, so our efforts now is to move into more available metals, no novel metals, and cobalt is a good alternative. Okay, if we are able to store energy, then we can create a completely new trade system of energy in the world, similar to the one that we have at the moment for fossil fuels. So those countries that have more renewable energy, and this map is showing solar insolation in the world, but we can also think about wind, we can think about any potential renewable energy, then we can start trading renewable energy in the world. This is very important because the challenge that we have is huge. We need to replace around 150,000 terawatts per hour of energy in the world. And for that, we need around 0.2% of all the solar radiation, but we need to capture that very efficiently. So we need as much as possible. So it cannot be a national effort. It needs to be an international effort, certainly. Okay, so with that, I'll come to the conclusions. So as I say, this is our vision. We would like to start talking about ammonia economy rather than a hydrogen economy. For us, is a fantastic carbon-free energy vector, and we know how to produce it in a green manner. We know how to use it for different sectors. But still, the research needs to focus on these two small arrows in this diagram. We need to redefine the Haber-Bosch process. We need to question how we do things and try to resolve it in an efficient manner. And the second thing is we need to know how to extract that energy later on. So with that, I would like to thank everybody in the group who has contributed to the work that we are doing on ammonia. Some of the collaborators, EPSRC for funding, and I'd like to thank you for listening.
Thank you very much, Laura. That was a very interesting talk, and thanks for giving that overview of your work. We've got a few questions coming in here in the chat. I'll start with the one at the top. So could you comment on how far the electrochemical synthesis of ammonia needs to move forward in terms of energy efficiency and cost to become competitive with Haber-Bosch?
Okay, very, very good question. So electrochemical synthesis, I didn't mention that. The problem with electrochemical synthesis is that you get hydrogen as a byproduct. So the production of hydrogen is more, is favorable compared to ammonia. So until we get that thermodynamics right, I think that we are not going to have a competitive technology there.
Okay. And someone's here is interested to know who you receive the most pushback from when you try to raise the profile of the green ammonia economy. You seek to disrupt one of the oldest and well-established industrial chemical industries out there. Great work. So yeah, where do you receive pushback from?
Well, we don't necessarily do it. So when we started working on this, people were questioning whether it makes sense from an energy point of view. So everybody knows that the Haber-Bosch process is extremely energy intensive. So if you don't make the calculations, it's difficult to convince people and say, oh yeah, it makes sense to store energy on a molecule that is very expensive to make from an energy point of view. But we have demonstrated that that's possible. And therefore, obviously, we can improve it. But yeah, it's promising.
Okay, thank you. And Hugh Hunt asked, ammonia for shipping, is that an easy win?
Oh, that's where most of the effort is at the moment. I can't say, I'm not an expert on shipping or engines, but I think that is certainly a place where ammonia is going to make a change very quickly. Yeah, we will see that in the next few years, certainly.
Great, thanks. And do you have an estimate for the efficiency of the ammonia energy process as a whole? How much of the initially captured energy is actually useful at the end point?
Yeah, that's the key question. This is where we get most of the pushback. I think at the moment the round trip energy is around 30%, 30–40%. So we still need these people working on electrolysis to improve our numbers, please.
Okay, great. I think we're going to have to move on there, but there's a few more questions for you there which you might want to answer in the Q&A box and type your answers. But thank you very much for your very interesting talk. So we're now going to move on to the next part of our symposium, where we've got 4 presentations from postgraduate researchers and early career researchers from a range of groups. So I'd first like to invite Dr. Molly Haugen from the Centre for Sustainable Road Freight to give her presentation. Molly, I can see you starting to share your screen already. Great. So over to you, Molly.
Great, thank you. Yeah, so I'm here on behalf of the Center for Sustainable Road Freight, but I predominantly work in Adam Boyce's group in the Department of Engineering. And today I'm going to be discussing a bit about the work I've been doing in conjunction with the Department for Transport in London. What I hopefully will give you at the end of this talk is an overall analysis of 2 different energy options for future fuels in the transport sector. There's a few different objectives that we wanted to identify and to assess in this project, primarily giving a whole system analysis to help decrease the cost, accelerate decarbonization, and increase energy security within the UK's energy system. From this, we first needed to identify and assess the severity of evidence gaps in future energy systems within transport. So in order to do this, we gave ourselves a few boundaries. And one of the main ones is that this work comes from a variety of literature sources, all the way from peer-reviewed journal articles to consultation reports, commercial information, etc. And we wanted to give it a national viewpoint. So there is work done on specific geographical areas. However, that's not within the bounds of this work. We really wanted to look at how to make stepwise decreases in greenhouse gas emissions for a large fraction of on-road transport, and specifically looking at on-road freight. This is done for a variety of reasons, primarily that cars and vans are likely to go electric. So we kind of just assumed that from the beginning. Rail is out of scope for this because those decisions will be made down the road. And then aviation and maritime are still really up in the air. So we wanted to focus on heavy good vehicles. And as you may know, there are 2 dominant options for this, both hydrogen and electric pathways. And we wanted to look at the energy system all the way from energy generation to energy use. So for this, a bit of background on the energy system analysis to start with, being that the energy efficiency of the overall system is going to really dictate how much of this infrastructure from energy generation to energy use is actually needed in the future. So this box represents the different components within the different energy systems that are analyzed. So for the hydrogen pathways, hydrogen can either be produced via steam methane reformation or electrolysis, as we've heard previously. It can then be distributed, either compressed or liquefied, and then through pipelines or on-road transport, then to the refueling stations, and finally to the vehicles themselves. Importantly here, that electrolysis can either be paired with renewable energy, or it can be paired with, say, the refueling station itself. So that would overall influence the end efficiency of this system accordingly. And then on the electric side, we go through all the way from energy generation to energy use as well. And these different efficiencies, these are the mean efficiency, or the most common efficiency for the currently available technology that's out there. We can get a total efficiency for the natural gas pathway, or for 2 different grid pathways, either through hydrogen or through electric. What this ultimately dictates is the amount of energy that can be used given a normalized energy at the very beginning. Meaning if there's a higher efficiency at the end, we need to generate less energy at the energy generation point. So this overall dictates the amount of infrastructure that's going to be needed for future energy systems that the UK implements down the road. To assess either of these different options, as far as from energy generation to energy use, I have a semi-quantitative study that looks at the risks and barriers associated with either of these options. So to give a brief run through of how this analysis works, I have an example for one of the linchpins or a key component that is essential within the energy system itself. So for battery electric vehicles that are operating on an electric road system or an ERS, there are a variety of different barriers that it needs to ensure that are in place for it to be successful. So along the top in the blue are the different barriers that each of these different components are going to be assessed off of. So technology readiness, this is how easily they can be implemented and how quickly they can come online. The scalability looks at the technology's ability to scale with demand over a long period of time. So this is looking at, as we increase our energy demand over years, how can the technology scale? Its geographical dependence, how dependent the different linchpins are on geographical location. System dependence is looking at system-wide integration of these different linchpins. Consumer acceptance, of course, this is a big one. If consumers aren't willing to opt into the different technologies, then it's going to be a hard sell. Resource requirements, what is the dependence of the technology on natural resources? Resilience, this looks at more minute fluctuations in the energy system. So for vehicles themselves, this is not a category that's assessed, but will be assessed further up the energy chain. Its ability to reduce CO2 emissions, of course, this is a big one. We want to make sure we're eliminating CO2 and not just moving it to a different geographical location. So if we're taking it off-road, we're actually eliminating it and not just displacing it. And then the consumer cost. So this is looking at the different costs that are associated with the different technologies on a consumer, industrial, and national level. So from here, we can start adding up the different linchpins that are in the different energy systems. So sticking with this battery electric vehicle pathway, we can also have battery electric vehicles that do not operate on an electric road system. So these would be independent of that. They have some scalability issues. Looking at their battery requirements is going to be a big influencer of how successful they would be in a energy system of the future. The distribution of electricity, so this is the charging stations or the electric road system, depending on the vehicle. With this, this is a slight geographical dependence for the charging stations. So where do they need to be located? So consumers are actually able to use them. And then for the electric road system, this is highly geographically dependent, being that the vehicles can only operate on certain given routes. We then have grid capacity and energy storage. So this is the energy availability going forward. One big issue with electric vehicles is the grid capacity, and it will be able to withstand fluctuations. So this is the resilient and resource requirements that are unknown in this system. Energy storage, of course, allows the energy to be available with the given technology. There's a variety of different options for this. I'm not going to go into detail with them here, being that we're kind of restricted on time, but there are a variety of options within the electric pathway. And then a real success story going forward is renewable energy. As Sam mentioned earlier, this is being reduced in cost, which is great. And we're seeing more and more of this come online. So that's a real win for any future energy system going forward. So this gives an overall look at an all-electric or an ERS, or electric road system, vehicle pathway. What you can see is that there are some areas that need to be worked out. There's some key linchpins that need to be answered before we can move forward, but the technology readiness and scalability are moving towards the green, or they're becoming less of a risk going forward. I won't go through the fuel cell electric vehicle pathway as in detail just due to timing, but what I hope you notice is that there are more more high risk areas that need to be assessed in order for this pathway to be successful. One big one is the hydrogen production pathways, both electrolysis and steam methane reformation with carbon capture and storage. These are relatively new technologies. Yes, there are electrolysis technologies that are online, but due to the intermittent nature of renewable energy, PEM electrolysis is really going to be key going forward in this energy system. Also with this, a big risk is the pipeline infrastructure that would be great if it could be reused. However, this will require a lot of research into specific pipeline components, trying to increase it with the energy demand requirements. So I'll just wrap up here with the key system knowns for both the hydrogen and the electric side of things, that renewable energy is decreasing in cost, which is great. And that on the hydrogen side of things, that maximizing the scale will also decrease the cost. On the electric side, a key note is that electric road systems can offer low carbon options to high traffic routes, which is a great option going forward. And then key system unknowns, these are areas that require a bit more work. Big ones here for the hydrogen side is the hydrogen production itself. And on the electric side of things, the scaling up of batteries. And so I realize I'm out of time here, so I will leave it there and hopefully be able to answer a few questions. And if not, please feel free to email me.
Great, thank you very much, Molly, and that was perfectly on time. So I haven't seen any questions come up in the Q&A yet, but maybe I'll just ask a quick question myself. So based on, I mean, clearly there were more, more oranges and reds, as you said, with the fuel cell route there. So do you, based on that, do you see a kind of future for hydrogen in the transport sector? Do you think it will be used? Or
I think there's a lot of conversation around it. So there are different areas that are pushing for hydrogen, or different companies that are pushing for electric. And I think understanding where that knowledge and where that that desire is coming from is important. And so that's what we're trying to highlight here. I think there could be potential use for hydrogen. I don't know if on-road transport is one of the areas for that. But people are looking at different options, whether that be shipping or in very localized communities. I think on a larger scale, there are better options.
Okay, great. Thank you very much. I think then we'll move on to the next speaker, but if anyone has any other questions for Molly, then please email her. So the next speaker is Aidan Parkinson from the Institute for Manufacturing. So over to you, Aidan.
Thanks. Just bear with me a minute.
And Aidan will be speaking on the social costs of carbon, the state of the art. So there you go.
Thank you so much. Wonderful stuff. Everyone hearing me all right? You can hear me all right, Eric? Yeah, great. Okay. Well, hello everybody. My name's Aidan Parkinson. I'm a senior research associate at Cambridge University Institute for Manufacturing, investigating executive education and Internet of Things. I'm also currently on sabbatical from a role as a professional engineer at Arup, and I own a micro startup called Realfeed Limited. I have a keen interest in global solutions for demand management and completed a PhD in building energy performance in 2016 at the Cambridge Centre for Sustainable Development. Am I sharing the right? Hopefully I'm showing that's the right screen.
Yeah, that's all good.
Yeah, okay. My talk is titled Social Costs of Carbon, State of the Art. The discussion has been developed entirely unsupervised by me and is yet to undergo proper peer review, and I make some really bold assertions. So and I'm also being quite playful with the title here. So some new ideas, and I'd appreciate some kind feedback if that's all right. If we briefly recap on the system we're trying to manage, just the basics of it. The carbon cycle occurs throughout planet Earth and is essential for all forms of life. The cycle involves exchange of carbon-based vapors with the Earth's atmosphere. Plants sequester carbon dioxide through photosynthesis, and animals and plants emit greenhouse gas emissions through respiration and metabolic processes. And industrial processes can also emit greenhouse gas emissions to deliver goods and services to support a growing human population's well-being. There is evidence of a governance problem with the carbon cycle on Earth from the British Antarctic Survey. Carbon dioxide concentrations in the Earth's atmosphere are now at the highest point they have been for 10,000 years, for one reason or another. These levels have risen to 140% since industrialization. This increase in carbon dioxide concentrations has been associated with global mean surface temperature increases, and further temperature rises may degrade the Earth's environment for human activity. We know since the time of Tyndall that carbon-based vapors may absorb radiant heat, and this suggests causality. This means that the activities I undertake privately release greenhouse gas emissions that contribute to a cost to all society globally, as a society as diverse in its taste and desires as its political organisation. So, how can I optimise my private greenhouse gas production? Economic theory would suggest I might add the costs of my greenhouse gas emissions borne by all global society to my own private costs when taking action. This would correct my production processes so that they are of maximum social benefit. However, in this context, I believe there may be different perspectives of what this social benefit could be. Notable, and actually in fact Nobel Prize winning presidents tend to take a utilitarian perspective. They prescribe aggregate or social welfare as a goal for social benefit. Aggregate welfare is not evenly distributed amongst the population. Pure reinforcement of aggregate welfare is largely in the interests of a few wealthy people. This approach typically employs Frank Ramsey's mathematical theory of saving as a decision-making tool, and this is presented here. This involves creating complex quantitative models of humanity's social and environmental systems using gross assumptions for evaluation. Welfare surpluses are then estimated for policy options by making projections of differences from the status quo hundreds of years into the future. Valuation of these surpluses requires setting a social discount rate, and this social discount rate requires a personal set of assumptions. This complex process results in social cost of carbon estimates that are uncertain for a historic time period using this method. The assumptions for a global social discount rate used for three notable contributions are provided in Table 1. Here. Mu is the social discount rate, which is similar in all three of these cases. However, the three contributions use very different assumptions for sigma, the difference in utility the wealthy gain from a unit of consumption compared to the poor, G, which is the long-term rate of economic growth, and delta, which is impatience to consume in fear of extinction. This yields very different values for the amount of surplus capital to be saved relative to that consumed, which is denoted by S here. Clearly, the worlds envisioned by just these three notable precedents are really quite different in nature, aren't they? Nobody has the power to actually set a social discount rate for all society. For most, these crucial assumptions are of private preference only. Notable modelling simulations returned a social cost of carbon of anywhere here between -$30 a tonne of carbon and $100 a tonne of carbon during the year 2010. The most difficult thing I have with this is that I'm not personally a utilitarian at all, and so find this method of estimation lacks relevance entirely to me. An alternative perspective is to use the principles of the social contract. Thomas Hobbes wrote a seminal book called Leviathan during the English Civil War. This book has been very influential in philosophers' understanding of the modern social contract. The principles of the book seem applicable to any form of government, be it liberal democracy, autocracy, or communist. Hobbes prescribes peace, promise, and rule of law as a goal for social benefit. Our problem is to value the social cost of greenhouse gas emissions as a good. Valuation need involve comparison of worlds with and without greenhouse gas emissions and stable currency. Our understanding of the carbon cycle helps us to determine that a world with greenhouse gas emissions, or a world without greenhouse gas emissions, is a world without life. For example, the moon is a world that is without a significant carbon cycle. Carbon is indeed an essential good we cannot do without. Our next task is to understand what underpins stable currency for a broad range of political organisations. Hobbes asserts that a natural condition of life is a war of all against all. Hobbes asserts that only through being in awe of a sovereign power who may rule on what is peace within a community can we have any faith in a promise and hence a stable currency. Sovereign powers require enforcement. They require enforcement to ensure peaceful compliance within a community, and they require enforcement to defend against competing externalities. Therefore, I believe in order to optimize my production processes to deliver a state of world peace and international currency stability, I need an estimate of present global gross expenditure on sovereign enforcement, and this will reflect sovereigns' future expectations. And I also need an estimate of global gross greenhouse gas emissions. And I simply divide the enforcement costs by the emissions. It is evident that this calculation requires just GCSE level math, but the accounting is not trivial at all. As a ballpark indicative estimate, I've taken an EU figure for gross arms spending globally in 2018 to estimate enforcement costs, which here is about $1.8 trillion. And I've divided this total by a Kyoto Protocol estimate of global greenhouse gas emissions in 2014, which was 9.8 gigatons of carbon. And I've found that this would yield a social cost of carbon in 2016 of something like $800 a ton of carbon. Clearly, this alternative estimate is of a different order of magnitude to even the high utilitarian estimates in 2010 of about $65 a ton of carbon and a 3% social discount rate. So, what might be the outcomes of adopting a Hobbesian perspective to this domain of decision making? I understand that the economic correction advocated here would be really quite substantial. The correction might be applied to every personal cost-based decision of anybody. And the energy performance gap actually would be much larger than I think many might accept, particularly those who use a lot of energy. However, there are some genuine appeals of this approach to me. I like the idea that anything can happen. This is a creative position. Most educated people can do the approximate math when pointed to the appropriate accounts, and we don't need actually distinguished professors from Yale and their computers. I do not feel the need to embargo anybody at all, and I have no idea what global surface temperature rise I'm targeting. To me, that question is now a moot point. That is not really my chief concern. And perhaps most importantly, my major criticisms here now rest with scientists, politicians, and public officials, which I believe are a healthy cause for appeal. So thank you so much for listening, and I'd be grateful to hear your thoughts.
Thank you very much, Aidan. That was great, and thanks for sticking to time as well. I haven't seen any questions come up in the Q&A yet, but people, please feel free to add your questions now. Just a quick question from myself. How do you think this suggestion would be, how could it be incorporated by politicians and governments, for instance?
I mean, there's a few ways of doing it. I mean, on like an individual level, if you had the information, you could just do it yourself. And actually, a private organization, if they had the information, could just implement it themselves, through their own private policy. But I mean, in a public sense, clearly, taxation is obviously, something that I think lots of people have thought about in terms of social cost of carbon and actually, affecting demand throughout an economy. And then also, I think, one idea I sort of came up with is the idea of, or not I came up with, I think probably other people have thought of it too, but is the idea of potentially, perhaps a bank or a financial institution having, this more significant social cost of carbon as an accounting requirement in their due diligence. So there might be, it might be projects need to be feasible in normal accounting, but also you could also make it a requirement that they need to be feasible with this social cost of carbon added. And if that were done, that then any loans made by that bank might potentially go to the right place. If that makes sense.
Yeah, no, fascinating. There's a few more interesting questions here come up in the Q&A now, but I'm in the interest of time, I'm going to have to move on to the next speaker. But I wonder if you could answer those questions in the typing option in the chat function. So thanks for submitting those questions to the people who did so. So we'll move on to the next speaker. So this is, it's now up to Collin Smith, who's a PhD student in Laura Torrente's group. And he'll be speaking on green ammonia for long-term energy storage. So Collin, could you please share your screen, and over to you.
Yes, so hopefully you can see that.
Yeah, we can see that. If you just make it into full screen presentation still. Perfect. Yeah, thanks.
So hello, everyone. So for my time here today, what I'd like to continue discussing something Laura mentioned in her talk, which is the redefining of the Haber-Bosch process for green ammonia synthesis and the work we've been doing in our lab to achieve this redefinition of the Haber-Bosch process. So just to sort of reemphasize what she was talking about, we're trying to pair ammonia synthesis with renewable energy. And because renewable energy is geographically isolated and very intermittent, it needs to be small scale, to be in diffuse locations, and needs to have response times that are fast so that it can accommodate quick fluctuations in the amount of energy that's being supplied, either through like a solar panel or a wind turbine. And then of course we also need it to be efficient, but as Laura mentioned, that mostly comes down to electrolysis, because that's particularly inefficient at this point. But mainly what we're going for is a small scale process with fast response time. So in achieving this, first we need to look at what the Haber-Bosch process looks like right now. And many engineers have already very familiar with the Haber-Bosch process, but to summarize, the key aspects of this process that haven't changed over the past 100 years or so is that you have this reactor that's operating at over 400 Celsius and over 100 bar, and it's achieving relatively low conversions, around 20%. So the effluent from this reactor needs to go into a heat exchanger to cool it down, and then to a condenser at below 0 Celsius in order to condense the ammonia, to separate it from the unreacted nitrogen and hydrogen, and then it is recycled back into the process with a fresh feed and then reheated back into the reactor. So because this process operates at high pressure, often much higher than 100 bar, up to 250 bar, in fact, and there's a significant heat exchange between the reactor and the condenser, what that means is this process is inflexible, it's meant to operate for a long time at steady state, and it's very capital intensive. So it's the exact opposite of what we're looking for pairing with renewable energy. So in trying to improve the process, the most obvious thing to try to do is to decrease the pressure, because that's one of the major limitations. And in fact, over the past 50 years, ruthenium catalysts have been very well developed in order to operate orders of magnitude better than the conventional catalysts at near atmospheric pressure. The problem is that the condensation separation becomes infeasible when you decrease the pressure, because the reaction equilibrium, as you can see on the graph on the left, becomes smaller very rapidly, and it very quickly approaches the vapor pressure of ammonia at -30 Celsius, where you would be condensing it, and below that you can't separate it. So what that means is when you go from, for example, we calculate here on the right, 150 bar to 20 bar, your amount of energy that you're consuming and your capital costs actually go much, much higher, because the separation is much more difficult. And at 1.5 bar, it's physically impossible because the equilibrium is less than the vapor pressure of ammonia. So decreasing the pressure with still keeping the condensation separation is not a viable option. Luckily, there's another option for separating ammonia that's become popular in the past few years, and that's absorption separation. What this is ammonia reacts with metal halides such as calcium chloride or magnesium chloride to form a complex. And because this is a really strong interaction, it can remove ammonia down to much lower pressures than, for example, the vapor pressure of ammonia at -30 Celsius, as it would be in condensation. effectively it can remove ammonia down to 0 bar, no ammonia. What this means is that you can now operate a process at moderate pressures like 20 bar. You can see here on the graph on the right, when we move from 150 bar to 20 bar using magnesium chloride or calcium chloride to separate, the process is still feasible. However, once you still try and go down to even lower pressures like 1 or 2 bar, it again becomes an infeasible process because the reactor is not producing enough ammonia each time you go through this loop. But most importantly about absorption separation is that it offers the possibility of combining ammonia synthesis and separation, which is what we are really trying to do. So with in situ absorption, you would be having ammonia synthesis and separation in a single vessel, and that would be the quintessential, let's say, low capital and agile process. You would have a single vessel that doesn't have any heat integration, it doesn't have a recycle loop. As you can see here in these figures, you would go from an absorption process that looks very similar to the condensation process with just an absorber instead of a condenser to something that has a single vessel with a reactor and absorber that you just pump in nitrogen and hydrogen, and then it operates in a semi-batch mode to regenerate the absorber and exhaust ammonia that is then condensed and collected. However, the problem with this, the fundamental challenge here is that reaction favors high temperatures, but absorption favors low temperatures. So you've got this balancing act that you need to sort of find a middle ground here where they're able to overlap with each other. In other words, you need to find a low temperature catalyst for ammonia synthesis and a high temperature absorbent in order to be able to combine them. And they'll be able to overlap. And in fact, we've been able to do this in our lab. We've proven this integrated process using, as I say, a specialized catalyst and absorbent. In our case, the catalyst is a ruthenium cesium ceria catalyst. So the cesium is a promoter for ruthenium. The catalyzing metal is ruthenium, promoted by cesium, supported on ceria. And this catalyst is able to achieve low temperature activity. As you can see in this graph on the right, it's down to almost 200 Celsius is where the activity starts. And it reaches high conversions quite quickly until at high temperatures, it then becomes limited by equilibrium. And then on the flip side of this, we developed a high temperature absorbent that is stable over many cycles. What that means is that it'll absorb ammonia and then you can release the ammonia many times and it's stable, it doesn't degrade or decompose. And the absorbent we developed for this is manganese chloride supported on silica, and was the one we found to be best. And what we found is that when you combine these two, as you can see in the graph on the right here, we are able to exceed the typical equilibrium for this process, because when we situate a catalyst and then an absorbent and then another catalyst, the absorbent takes out the ammonia, and then the second catalyst bed is able to make more. So it's able to get past where the equilibrium was originally. So you can see here, with one layer of absorbent, we're able to get up to, say, 22 or 23% conversion, whereas equilibrium is down at 15% conversion or thereabouts. And then we can do even better. We can add 2 layers of absorbent. So we have the absorbent catalyst twice. Each time ammonia is removed, and then the catalyst makes more ammonia. And then we can get up to almost 30% conversion. So in conclusion, we have proven that you can combine synthesis and separation of ammonia into a single process. And we think this constitutes a significant redefinition of the Haber-Bosch process, because effectively what we would be doing is going from a large-scale capital-intensive plant that looks a lot like something on the left, which is an actual ammonia plant meant to operate at steady state and really expensive, to something that is in a single vessel, that is simple, it's agile, and it's low capital, obviously, because it's a single vessel operating at relatively low pressures. And we think this is a significant redefinition of the Haber-Bosch process, allowing ammonia synthesis to be made with renewable energy, such as a solar panel or a wind turbine. Thank you, and I'm happy to take any questions.
Great, thank you very much, Collin, for your interesting talk, and thanks for sticking to time as well. I have if anyone has any questions they would like to submit in the Q&A now, then here's your chance. But I've got a question just in the meantime. So this, I mean, it sounds like you've got these new catalysts to do this in a single process. But what is the kind of, how do you think you can upscale this to do this, to do this at larger scales? Is that, how easy would that be?
So, I mean, an important question that needs to be asked from this point on, now that we've proven it, is how large of a scale do we actually want? Because with this sort of a process, it's actually possible to, for example, have a very, very small scale ammonia synthesis plant. For example, a office building or something like that could have solar panels on its roof, and it could be storing that energy in the form of ammonia using this small ammonia plant. So we're completely rethinking the scale of this. We're not thinking in terms of huge tons per day of ammonia, which is what most plants do. We're thinking in terms of a much smaller scale and meant to be paired directly with renewable energy.
Right. Yeah. Okay. So you'd have more like smaller off-grid almost.
Yes, exactly. It's ideal for off-grid.
Yeah. Okay. Great. That's really interesting. Thank you very much. If anyone has any further questions for Collin, please add them in the Q&A still, and you can answer in typing. And I will then move on to the final speaker of today, is Dr. Sergey Kolesnikov from the Synergy group. And he's be speaking on how technology spillovers contribute to clean energy innovation. So Sergey, over to you, and please share your screen.
Thank you, Eric. Thank you for this opportunity to present our results for Cambridge Zero community. So I'm a postdoc in the Cambridge Center for Environment, Energy and Natural Resource Governance, which is a part of Department of Land Economy. So before I start, a couple of words about our center. We were founded in 2014. We conduct integrative research on the governance of environmental transitions. And we have three major research areas: climate change and energy policy, conservation and biodiversity policy, and environmental law and governance. So I work in the first group on climate change and energy policy. So what does it have to do with clean energy innovation? The thing is that we view it as one of the key elements on a pathway towards decarbonization, and industrial and innovation policy as the key enablers. So we want to understand how clean energy innovation works and what is the role of policy in it. And in this case, we focus on a particular phenomenon, which we call technology spillovers. So it is often the case that innovation in clean energy comes from unexpected places, from other technologies, from other areas of research, which were not directly, which were originally not intended for energy applications. Nevertheless, they become important and they play an important role in clean energy innovation. So, for example, when in the mid-1990s, blue light emitting diodes were first developed, it was not possible to use them as a source of general lighting because, well, nobody wants to live under the blue light. So it took a Japanese chemical firm, Nichia, to apply a phosphor, a chemical used previously in fluorescent lighting, to convert blue light to white light. And as a result, it enabled the development of white LED lighting devices for general illumination purposes, which are now the core of the whole solid-state lighting industry that we know today. Similarly, carbon fibers were originally developed for automotive and aerospace applications, and now they're being increasingly used as a material for the blades of wind turbines, making them more lightweight and durable. So this phenomenon is called knowledge spillovers, which is knowledge developed for one purpose or in one socio-technical context, finding application for a new purpose or in a new context. International Energy Agency predicts that knowledge spillovers will play a critical role in the development of clean energy technologies that will contribute up to 30% of cumulative emissions reductions up to 2070. So we clearly need to understand how clean innovation works, how we can accelerate it with policy or R&D management practice. And for that, we need to understand how knowledge spillovers work. As a first step in this direction, we ask ourselves the following question. So how knowledge spillovers across technologies occur? How do they contribute to clean energy innovation? What factors enable or affect them? And ultimately, can we leverage spillovers to accelerate innovation? So we do it as part of the 3-year project funded by Alfred P. Sloan Foundation in the US. So we partner with Harvard University, University of Minnesota, and also our colleagues at ETH2. So the project focuses on 3 low carbon energy technologies: solar photovoltaics, lithium-ion batteries, and solid-state lighting. And in the part of the study that I present today, we develop a conceptual framework and a known methodology for identifying and analyzing the individual technology spillovers as a process. As a preview, we find that technology spillovers enabled many solar PV innovations, and policy played a critical role in enabling them. So how did we do it? At first, we developed a conceptual framework for analyzing technology spillovers, in which we define technology spillover as a process of boundary spanning knowledge transfer between technology domains that drives technology change in the recipient technology domain. We can visualize it using a metaphor of inelastic collision. So we can imagine a technology moving along a certain technology trajectory, which interacts with external knowledge, which changes the trajectory of technology, ideally leading to an innovation. So based on this framework, we identify 6 key spillover features listed here. We identify appropriate research methods to identify and analyze each of these features individually, and then we bring them all together in a mixed methods approach to study and analyze technology spillovers that combines insights from the literature review, expert interviews, analysis of citations in publications and patents, and also machine learning-based topic modeling of patent full text. So we bring insights from all those methods together to create process tracing narratives for the innovation of in the focal domains in which we're interested in. And also we visualize them with maps, such as this one, which we show for a subset of technologies in crystalline silicon photovoltaics, namely ion implantation, pulse annealing, and laser doping. So that's a complicated picture. You don't have to look at all the details here. I would just like to highlight the following findings. So first, spillovers, represented here by light blue arrows, were happening at multiple stages of innovations, multiple times throughout the whole history, 60 years of history of these technologies. Second, some of the spillovers play the key enabling role in those technologies. So without them, technology would not have existed. And the third thing that I want to point out here is that for almost all of the spillovers, policy played a key enabling role to enable these spillovers and corresponding innovation. And it depended, the role of particular policy depended on the stage of innovation. So in early stages, it was mostly R&D funding, such as defense funding or energy funding from the US government. Later, there was funding for government funding for industrial prototypes in US and Japan. And more recently, in 2010s, the latest spillover, which finally brought ion implantation in photovoltaics to the market, was driven by market dynamics. So we all know that there is a continuous rapid decline of cost of PV technology, which made this technology cost competitive. And this attracted attention of semiconductor industry, and they started producing they started to produce ion implantation equipment for specifically for PV applications. But this market dynamics would be impossible without renewable deployment policies, such as the German feed-in tariff implemented in 2000 in Germany. So What can we learn from these pictures? First is that technology spillovers can enable technology. They can contribute to advances in technology at every stage of innovation. We also found that they can happen either in a targeted knowledge search or in undirected blue sky research. So there are clearly different mechanisms by which spillovers can happen. So we need further research into the spillover mechanism. On the policy side, we found that public funding for research, development and demonstration, as well as renewable deployment policies were key enablers of spillovers in this studied subset of solar PV innovations. So different stages of innovation require appropriate policy tools to enable spillovers. Finally, we found evidence that stop-go funding cycles negatively affect spillover integration and time to market. So in this case, for example, in 1981, there was a large-scale defunding of the solar PV innovation program in the US Department of Energy by Reagan administration. And there is strong evidence that it delayed market entry for some of those technologies for at least 30 years. So funding should be continuous and stop-go funding cycles are bad. So with all those insights, we can affirmatively answer the question of can we leverage technology spillovers to accelerate clean energy innovation? But well, the next question is how do we do this? And well, this will be the subject of our future research. And with this question, I would like to leave you for now. And thank you for your attention. So one final note is that an expanded version of the talk with the details of that history that I presented, and also including our results on lithium-ion battery and solid-state lighting, will be presented as part of the Synergy Seminar series on 18th of March. And if you're interested, you are very welcome to register during the following week. Thank you.
Thank you very much, Sergey, and thanks for sticking perfectly to time as well. And please, if you send me the details for your seminar as well, we will circulate that to all attendees so people can find that link. So if anyone has any questions for Sergey, please enter them in the Q&A now. I just have a quick question myself already. I mean, I guess with these spillovers, what's inherently really hard about them is from my understanding anyways, that they're very hard to predict when they might happen, right? Or is it even possible to predict these, you know, where do you think a spillover might happen, and can you target them in any way?
I think it is more or less hard to predict at the research stage, but we definitely need to be on the lookout for them at later stages of innovation. So if we see that something is happening at the stage of research, then maybe we can look more closely at it, experiment it in the process of technology development at the demonstration stage. So, in fact, some of the recent reports, such as the International Energy Agency report on clean energy innovation, which came out last summer, it makes these predictions that certain technologies will be important in bringing some of the technologies to the market. So we can make early predictions by looking at what is happening at the research stage. Well, at research stage, it is harder to do, to predict what will be the source of this sudden new knowledge that can come in. And that's actually a very interesting question that we want to study next. Basically, what were the mechanisms that brought this spillover knowledge into the focus of researchers' interest? So how did they learn that something existed? So was it some kind of a chance finding, serendipitous finding, or was it a targeted search in certain domains? And how did they, well, decide where to look for?
Okay, great. Thank you very much. So, okay, I think we will, I haven't seen any other questions come up, but if anyone has any questions for Sergey, please email him or indeed attend his talk on the 18th of March for more information. So I think we'll close our seminar, our symposium there, and that was because that was the final talk. So I would just like to finish by saying a really big thank you to all our speakers who all, you know, for all giving really great talks and sticking very well to time. And we've actually got 1 minute to spare right now, so that's perfect. So thank you all very much. Thanks for all the questions that came up in the Q&A, and also to the speakers for answering those questions both live and in the chat function. And I'll just quickly bring back up my screen here, if I can get it to work, with our So the following options here of how you can continue the conversation with us. So there's, I would definitely like to highlight later this week on Friday, there is the Energy Transitions Discussion Series. They have their first event taking place on Friday, which will be focused around batteries and energy storage, which was one of the topics that came up a lot today. So please do register to attend that event to join in there. Next week, we have our next Cambridge Zero Research Symposium on Health and Society, which takes place on Wednesday, the same times as today. So please go to our website and you can sign up there, and we will also send the sign up link for that symposium out to all of you. And please also sign up to our mailing list if you haven't already. Again, we will share that link, and please do follow us on Twitter as well. So those, I think with that, I would like to leave it there and thank everyone for joining and thank everyone for attending, and hopefully see you all next week at the following symposium. So bye from me and thanks a lot. Have a good evening.